What was lesson 12? Non-singular linear systems. Huh. Doesn't that seem so random? I wonder if you could state what a non-singular linear system is. Yeah, so what do we need to define a non-singular linear system? We need a matrix be a given non-singular matrix. We're not really sure what non-singularity means, right? Yeah, non-singularity, we will learn that that's called invertible. That's called that's called lesson 14, what you just said. Let me give you a fast way to think about this. Linearly independent columns. So it's kind of a really, really special matrix. It's a square matrix whose columns are linearly independent. So that's a fast way to think about it. We'll learn why we spend so much time studying those particular matrices as we move on in this course. What's the fast way to think about a non-singular linear system? It's a backwards problem. Okay, so yeah, let's do it. So we have A is a square matrix with linearly independent columns. And then we have a B element of Rn. Let's suppose right now that it's given. Then the NLSP, the non-singular linear systems problem, is to find what? Unknown x in Rn such that what is true? A multiplied by the vector x is equal to the vector b. When we're thinking about, let's imagine for a moment that we were in the paradigm that we started with. Oh, I suppose I should do the color coding. Underneath both of these problems, we have this very special function called the matrix vector multiplication function. And in this case, we had something quite special about that. So this was called the matrix vector mult function. What do you think? Is that function really, really simple, or is there a lot going on there? Yeah, much more so. I remember one person in week 3 was like, well, this class is going to be really easy, I can tell. And then I just kind of smiled. Because it seemed really easy in the beginning, right? Because I've worked like 6 years of my life to make it look easy, right? So that we could kind of ease into that. Okay, so let me ask you this. When we're doing the forward problem, where does this function come from? Where does it go to? What's the size of the input there? Rn. What's the size of the output? Rn. And remember, we're mapping from the input to the output. In the matrix vector multiplication problem, what do I give you? I give you the input, and then I map forward to the output. That's called the forward problem. How do I actually solve that using stuff from lesson 6? I take a linear combination of the columns of A using scalar coefficients from the rows of X to produce the vector B. Okay, so that's called the forward problem. And the really, really special information about this, in the non-singular case, the columns of A are linearly independent. So what does it mean for the columns of A to be linearly independent? No, we'll come back to that. We'll come back to that. That's not an easy question, right? The linear independence is quite a subtle thing. What then is the backward problem? So I give you a vector, and then what do I ask you to do with that vector? Well, yeah, okay, that's the function definition, but I want you to do the linear combination discussion. my claim is you've actually already solved your first linear systems. It wasn't a non-singular linear systems problem, but on problem number 3, I think, on the last test, remember I gave you 3 vectors, and I said, can you write one of the vectors as a linear combination of the other vectors? Yes. And then I said, please produce the scalars. Yes. That was a linear systems problem. Because I gave you a vector, and then what did I ask you to do? Find a set of scalars such that when I multiply the columns of the matrix A, so if I think about the matrix A as a set of columns, each scalar that I'm searching for, I'm going to multiply by the appropriate column, and then I'm going to do the entire linear combination. And the claim is, if I solve the linear systems problem, when I take that unknown and desired linear combination, what should I produce out? The given vector B. So it's the reverse of this one, because in this one I gave you the scalars, I gave you the vectors, and I asked you to produce the linear combination. In this one, I gave you the linear combination, I gave you the set of underlying vectors, and then I asked you to produce the set of scalars, right? The set of things underneath that I need to multiply by, so that when I add all those products up, I get the original vector that I came from.